Hello and welcome to the section where we will be going over exponent rules. Yes, there are rules dealing with exponents. We're going to first review the first three E's of exponents. So when we had something like 2 to the fourth power, this was what we called in exponential notation. This guy right here was called the base, and that guy right there was called the exponent. And then together that's called exponential notation. So that's the first E, exponential notation. When you expand this out, what this really means is 2 times 2 times 2 times 2, and this happens 4 times over. A repetition of 4 timesing of timesing 2 by itself 4 times. So that's called expanded notation. So that's the second E, expanded notation. And then when you evaluate it, you get 16. So this is called expanded notation. Expanded. And then this guy right down here is when you evaluate it. And the nice thing is when you have numbers, you can evaluate them. You can stick them into the calculator. And as a reminder, this is what the calculator looked like when you did it. You did 2, and then the exponent was this caret looking thing over here. And your calculator may have something different. It may have an x to the y button or something like that. 2 to the fourth power, and you'll see it comes up with 16 indeed. So that's exponential notation, expanded notation, and when you actually evaluate it out like that. Well, that's our third E. When we have it in exponential notation, like with variables, we will have a way to simplify things. And it's kind of weird. Like if you have x to the third power, that's an x times an x times an x, but you can't evaluate it unless you know what x is. And if they say, oh, if x is 2, then you stick a 2 in there and you get 2 to the third power, or cubed. Okay, so with that, we're going to immediately be able to come back to the first law here. If you have 2 to the first power, well, that's 2 times itself one time. It equals 2. 7 to the first power is just a 7. So similarly to the way, when you see a number and you're like, oh, you could write it as a fraction over 1. There is an invisible 1 right up there that you can write if you so choose. If you ever see something to the first power, it just means that it is that number. And so that's the first law. Any number, x to the first power, is just x. So these two are exactly the same thing, and that's what that one law is all about. So now we start to see that there are ways you can actually simplify things. For example, if we have x squared times x to the fifth power. If we multiply these two things together, we don't even know what x is, but there is a way to simplify it. And we can do it the long way. Let's write this guy out expanded. That's x times x. And then we're going to be timesing it by x times x times x times x times x. 5 times. So here we have 2 of them, and here we have 5 of them. Well, look at what we have. All of these x's are multiplying together. How many total x's do we have together multiplying themselves? We have 7 of them. So the shortcut is that we would have x to the 7th power. And you're like, wait a second, does that always work? Let's try it again. If we have a to the third, a cubed, times a to the 8th power, what do you think the answer might be? You're like, well, if it works the same way, it'll be a to the 11th. Well, let's check it out. We have a, and then we have 8 more. 1, 2, 3, 4, 5, 6, 7, 8, which gives us a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Indeed. And that is the rule, that you will take these two. If these bases are the exact same base, then this is just counting up how many a's we have here, how many a's we have there. So together, you add the exponents when you are multiplying. So the product rule means that you add the exponents when you multiply. We're going to try it with some actual numbers. If we took 2 to the fourth power times 2 to the fifth power, that should equal, if this rule holds, 2 to the ninth. Notice it's not 4 to the ninth. This is counting up how many 2's we have, so it's that 9 is the number of 2's you have. Let's see if that actually works. That's 2 to the fourth, and then 2 to the fifth is 32. So this is 16 times 32. 16 times 32. is 512. Now, if I punch in 2 to the ninth, then that, boom, math is true. Let's try it. 2 to the ninth power. And is it going to work? Yeah, it works. This is a bona fide rule that it works with any numbers. X's, A's, 2's, 7 to the third times 7 to the fifth. That's 7 to the eighth power. You will add these exponents. And so this is how it will be written in a book. You'll have something like x to some power m times x to some power n, or an a or a q or whatever variable they choose down here. And you can combine these two together by saying there are m plus n of those up in the exponent. So 2 plus 5 is 7, 3 plus 8 is 11, 4 plus 5 is 9, 3 plus 5 is 8, and it will always work that way. That's pretty cool. Multiplication between exponential expressions results in addition of the exponents. So what happens if we divide? What if we took this and went backwards? X to the seventh over x to the second. Well, if x squared times x to the fifth is x to the seventh, then x to the seventh divided by x to the squared better be x to the fifth. If multiplication leads to addition of exponents, then division better lead to subtraction of the exponents. Let's do this in slow motion, just like we did out here. If we write this in expanded notation, we have 1, 2, 3, 4, 5, 6, 7 over 1, 2. Well, these are multiplied to each other, and this big long bar here means division, which means that guy goes out with that guy, and that guy goes out with that guy, leaving just a 1. These divide to 1, and so we get x to the fifth. That's correct. So what if we did, let's take this a problem and write it out a little different. What if we had a to the 11th over a to the third? Well, 11 minus 3 is 8. That's the quotient rule. If you have, let's write this, x to the m over x to the n, it ends up being m minus n. Oh, I love that. All right, let's erase this and work on to the next one. In leading up to this negative law, we've got to do this one a few times and see what actually comes out. If you have something like x to the seventh over x to the third, this rule says you take that one minus that one. 7 minus 3 is x to the fourth. A to the fifth over a squared. 5 minus 2 means you have 3 of them left over. B to the ninth over b to the sixth. 9 minus 6, you'll have 3 of them left over. Let's do it one more time. Q to the 15th over q squared. You have 15 q's all timesing together up here, 2 q's timesing down here, and you end up with 15 minus 2, 13 q's left over. Well, what happens inevitably is that when you start subtracting, I don't know if you remember this back in arithmetic, but you started subtracting and eventually you ended up with negative numbers. Oh boy, what happens here if we do x to the third over x to the seventh? Well, based on this rule, instead of 7 minus 3 equals 4, we got to do 3 minus 7. That's an x to the negative 4 power. Over here, if we switch those two places, if we have a to the second over a to the fifth, that is a to the negative third power. 2 minus 5 gives you a negative 3. 9 minus 6 gives you 3. So if you flip those over, b to the sixth over b to the ninth, that's a b to the negative 3, and so on. When you subtract them, you might end up with negative exponents. And then, what do you do with the negative exponent? That should cause you to think a little bit. How do you times x by itself a negative number of times? That doesn't even make any sense. So let's go back to the slow motion way of doing things. If we had 3x's and 7x's, oh, there we go, 7 of them, and we cancel them out, that divides to 1, that divides to 1, and that divides to 1. Notice that we have x to the 4 on the bottom and 1 left over. This is 1 over x to the fourth. Now, this takes a little bit of getting used to, but a negative exponent, based on this subtraction rule, has to be exactly the same as putting it on the bottom. That's weird to see. Again, if you took 9 minus 6 with more b's on the bottom, that just means you ended up with 3 b's on the bottom timesing together. B to the negative 3 equals 1 over b cubed. Fascinating. This is very important, but it's a confusing law at first. This one is the same as 1 over a to the third. It's just when you divide these out, the 3 left over are on the bottom. Whichever one is bigger wins. It's just like subtraction normally. So a negative exponent is not considered simplified. You always need to flip it like that. And so this rule will often be called the elevator rule. And what it is if you have x to any like negative a power, it's 1 over x to the a. So it flips it. It moves it down to the bottom, or if it were on the bottom, it would move it up to the top as a positive exponent. Let's go through a couple of examples with numbers and show you how this works. If I punch in 2 to the 4th on a calculator, we just did that, and let's punch it in one more time, make sure we have it here. 2 to the 4th power is 16. Now if I write 2 to the negative 4th power, that's got to be, according to this rule, if I write 2 to the negative 4th power, that's 1 over 2 to the 4th power. Elevator rule, you flip it. And so it better be 1 over 16. You're like, really? I don't know if that's true. Let's try it. 2 to the negative 4 power. Ooh, it's a fraction. Do we know how to turn things into fractions? Yeah, we can do that. Oh my word, that decimal is exactly 1 over 2 to the 4th. Let's try it again. What is 2 to the 3rd power? Well, that's 2 times 2 times 2 is 8. Just double checking our calculator. 2 to the 3rd power does 2 times 2 times 2 is 8. Now what if we did 2 to the negative 3rd power? It's a fraction. Now if we take and change that guy into a fraction, it's 1/8. 2 to the negative 3 is 1/8. Yeah, notice that 2 to the 4th and 2 to the negative 4, they're just reciprocals of each other. Let's try another with 2 squared. 2 times 2 is 4, so 2 to the negative 2 power better be 1/4. Ah, fascinating. Let's double check that. 2 caret negative 2, that's 0.25. Turn it into a fraction, and it is 1/4 indeed. That's the idea of the elevator rule. Very cool. So anytime you have a negative exponent, move it to the bottom, or if it were on the bottom, move it to the top, and you'll have it down. This final law flips people's minds over on their head. It's just a crazy experience when they see something. I'm going to put out a number for you. 3 to the 0 power. And initially, you'll think that might be 0. You think that might be something else, but that's actually, well, let's plug it into a calculator and see what it is. 3 to the 0 power, and I hit enter. 1. What? 3 to the 0 is 1. Were you thinking it might be 0? Yeah, that's a really common thing. Try this other one. 17 to the 0 power. What do you think that equals? 17 to the 0 power, 1. What? This is the weirdest law in the world. Any number to the 0 power equals 1. You just saw that on the calculator. You could take 293 to the 0 power, and it equals 1. And that should kind of surprise you. So let's go through and use these other rules, and we'll show you how this has to work. All right, so first of all, we're going to show you with this quotient rule. So we know that if we have something like x to the 5th over x squared, 5 minus 2 is x to the 3rd. 5 minus 2 is 3. Now, if I do something crazy like x to the 5th over x to the 7th and I subtract it, I get a negative exponent. But what if I take x to the 5th over x to the 5th? You're like, well, anything over itself is 1. Yes, that's correct. But if we follow this rule exactly, we're going to get x to the 5 minus 5 is 0 power. But you know that that's 1, and you're like, wait a second, something's going on. But that's exactly true. The only way to get a zero exponent is by making sure we have divided off everything we've times by. That's how we get a zero exponent. All right, let's try another one. If we take like y to the 8th power over y to the 8th power, 8 minus 8, that's y to the 0 power. But what is anything divided by itself? 1. All right, let's try it again with the product and the negative rules. So we know that x to the negative 3 times x to the third, that has to equal negative 3 plus 3. That has to be x to the 0 power based on the product rule up here. But we also know that x to the negative 3, elevator rule, that's 1 over x cubed times x cubed. That's going to equal, that's over 1. X cubed over x cubed, same thing, and it equals 1. So look at this, x to the 0 equals 1. Holy cow, let's look at it with numbers. You remember we wrote up there a 2 to the 4th and a 2 whatever. Let's do it with the 3 so we can see this work. 3 to the 4th. Plug this in your calculator and you get 3 caret 4 is 81. So I'm going to fill all of these guys in just a minute. 3 to the 1, 3 to the 0, 3 to the negative 1, 3 to the negative 2, 3 to the negative 3, 3 to the negative 4. Okay, now 3 to the negative 4 we know is 1 over 81. Now we could try this if you wanted to again. 3 caret negative 4 is that ugly thing. And if we turn that into a fraction, 1 over 81 indeed. Okay, so 3 to the third power. This is 3 times 3 times 3 is 27. And so 3 to the negative 3 has to be 1 over 27. Again, it just flips it onto the bottom. 3 squared is 9. 3 to the negative 2 power is 1 over 9. Should we do those just to make sure? 3 to the negative 3 power and turn that into a fraction. 1/27th. 3 to the negative 2 power and turn that into a fraction. 1/9. Indeed. Yeah, it's working. See how these are exact reciprocals of each other. 3 to the first, our one law, that's 3. 3 to the negative 1 is 1 over 3. Now, I want you to notice this pattern. Every time we increase a power, that means we're taking 3 times 3, 3 times 3 times 3, 3 times 3 times 3 times 3. We times by 3 by moving up this chain. Moving down this chain, we divide by 3 each time. And you can try that. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. Now, if you take the question is what needs to go right here to fill in this pattern. If you're dividing by 3 each time, 3 divided by 3 is 1. 1 divided by 3 is 1/3. Divided by 3, divide by 3, divide by 3. And it works. This is the only number that can fill in that hole exactly. Which brings up two major points. Number one, anything to the 0 power is the number 1. It's not to the first exponent, it is the number 1. You can try it with 17s or 293s or whatever. The other thing is that negative exponents don't create negative numbers. They just create really tiny small fractions. So when you get to scientific notation, that'll help you to identify that, yeah, when you have a negative exponent, you're going to have really tiny fractions.